Hey everybody, I wanted to show you the relationship between Ka and Kb. Now that we kind of understand that acids and bases, weak acids and weak bases have certain reactions, I wanted to spend a little bit of time showing you what that relationship is between these two things. So, okay, Ka and Kb. If you look in the back of your book, you can find a whole bunch of Kas. Okay, there's lists and lists and lists. If you go to, you can find Kas. They never list Kbs. Kbs are never listed because if we take a Ka and multiply it by the Kb, it will equal Kw. And remember, Kw is 10 to the minus 14. Okay, so Ka times Kb is 10 to the minus 14 as long as you're dealing with the conjugates of each other. Okay, so what do I mean by that? Well, let's take a look at this is going to take a little bit. So if we look here, you can kind of see that this is HF, and then its conjugate is F minus. Here is HC2H3O2. That is its conjugate here. You lose the proton. Or if you have ammonia, okay, its conjugate acid is this. Now, you have to be careful here because when you convert between Ka and Kb, yeah, they're related, but it's not for the same reaction, okay? So let me show you how this works. Okay, so let me tell you kind of what we do know. That we know that Ka times Kb equals Kw. Okay, now Ka is the acid equilibrium constant, and so we know that we should never change the acid reaction. So let's say that we have acetic acid. Okay, acetic acid is HC2H3O2. It's got its ionizable H, it's weak, and so in this, what we do is we react this with water. Okay, when we do that, that is in equilibrium with the hydronium ion. Sometimes that happens, I don't know why. Let's see if I can redraw the hydronium ion plus the acetate ion. Okay, now we can look up the Ka of this reaction. Look, you have the weak acid, its conjugate base, you have water. If this is an acid, this is acting as a base, so it's going to accept a proton. There's all sorts of things that we can review and look over, but what we know is that the Ka for this reaction equals 1.8 times 10 to the minus 5. Okay, well, if the Ka equals 1.8 times 10 to the minus 5, we can do some quick math and we can figure out what the Kb is. So we do Ka times Kb equals Kw, 1.8 times 10 to the minus 5 times Kb. I guess that sometimes this happens here. Okay, times Kb equals 1 times 10 to the minus 14. Okay, so now we divide 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. And when we do that math, when we math that, we get Kb equals 5.56 times 10 to the minus 10. Now that's for the Kb. Now that is not for the opposite reaction. That's what we got to be careful of. the opposite reaction doesn't form the hydroxide ion, which is going to change the pH. What that is that's the Kb for the base reaction of the conjugate. What is the conjugate? It's this guy. So that base reaction is going to be the conjugate C2H3O2 minus plus water H2O is in equilibrium with OH minus OH plus. I always make those silly mistakes here. OH minus plus HC2H3O2. And it's because we're producing hydroxide that this is a base reaction. Okay? So keep in mind that while Ka and Kb are related, the acid and base reactions are different. We just follow the rule that the acid reaction never changes. From what we know, it's always the same. Acid plus water gives us hydronium plus the conjugate. And the base reaction will never change. Base plus water gives us hydroxide plus the conjugate. Okay? So, keep that in mind. Now, as we move along, if I can get this, see how weird this is being, let's look at something really quick. Okay? And so what happens is if we have a conjugate all alone, okay, so an anion, which is a negatively charged ion, okay, if we have an anion alone in water, this thing is possible to have a pH, to change the pH. Why? Because anions can produce hydroxide ions when they react with water. Okay, so if we have something like F minus, okay, well F minus plus H2O gives us HF plus OH minus. This guy takes a proton from water, giving us the hydroxide. Now the key here, and this is how you can tell what's going on, the key here is that HF, the conjugate, must be weak in order for this to have a pH. Okay, I'll give you an example of one that isn't. Okay, if we have bromide ions floating around in water, so we have bromide plus H2O. Okay, this could react to form HBr plus OH minus. But what's the problem here? This guy, as we're looking at it, this guy is strong. And what do we know about strong acids? They completely ionize, they completely dissociate. So the chemistry behind this is, since this completely dissociates, there's no HBr around. So it's H plus and Br minus. The H plus and the OH react to form your water, and the Br is still forming around. So if it is the conjugate of a strong acid, okay, it's not going to change the pH. Only conjugates of weak acids will change the pH. Now, here's the funny thing. Which way does the pH go? Well, F minus, when it undergoes the reaction, will get a proton. It'll produce the conjugate, but it's producing hydroxide, so the pH will go up. Okay? The pH will increase. Okay. So now the opposite is also true when we're dealing with bases. Okay, ammonia. Okay, let's look at this. So this is a weak acid, or weak base now, NH4 plus. And if we want to get an idea of whether it can be an acid or a base, we're going to react it with water, H2O, and that's going to be equilibrium with, well, what's going to happen? Well, this isn't going to get a proton because it's because this proton is because it's already a plus charge. So pluses aren't, it's only opposites that attract. So this is going to, so water is going to act as an acid, and it's going to gain a proton, H3O plus, plus NH3. Now, again, here we have this guy, which is a weak base, but what is being formed in the reaction? The thing that's being formed in the reaction is hydronium ion, which is an acid. So when you react with cations, cations have a tendency to lower the pH. The pH will go down. And just like with acids, bases are the same way. Strong bases, conjugates of strong bases, do not change the pH. Okay, so real quick, this one's a little bit different because you have OH minus plus H2O. Okay, all the strong bases are completely, so I'll go one better here. Okay, so what if we have lithium hydroxide plus this? Well, when this reacts, you're going to get lithium hydroxide plus H2O. Okay, because the hydroxide switches with water. Water can be rewritten as HOH. So this hydroxide takes this proton, and this lithium associates here. So there's no net change in the reaction. So again, it has to, in order for the pH to change, it needs to be a weak base, or the conjugate of a weak base, in order for it to change. Okay. Strong components keep the pH the same. Okay. So I hope that clarifies some of the ideas about the relationship between Ka, Kb, and Kw, and how cations can change the pH of water.